This is a presentation of Welcome Molalla, where we bring you fun and informative videos from within our community. In today's episode, we continue with our local geology tour of the Columbia River Basalt Group and follow it west and south from the Molalla River corridor, a video that we presented back in episode 8. This video features Sheila Alfson, a geology professor at Portland State University, and Bob O'Black, Mollalla's own geology enthusiast.
Hi, I'm Bob O'Black. I'm going to continue the story of the Molalla River corridor lava flows. These were presented in episode 8 of the Welcome Molalla videos found on both Facebook and on YouTube. So conceptually, you can think of the Molalla River corridor as the city of Mollalla's backyard. It's a few miles east of the city limits, and it offers many points of interest from a geologic point of view. And it offers just outstanding natural beauty, and it's all in our own backyard. So in this video, we're going to venture west and south of Molalla into our front yard. We'll follow the Columbia River Basalt Group west and south and examine the geologic points of interest on its way to the Pacific Ocean. So as we leave the Molalla River corridor, our first stop is a rock quarry northwest of Salem.
Hi, my name is Sheila Alfson, and I'm a geology professor and K-12 teacher, and we are standing here in the Amity Hills. And the Amity Hills are a northern extension of the Eola Hills. And what you see behind me, you can see all this beautiful basalt and those really distinct columns here. And we've got about 150 feet here exposed in the quarry here. Now this basalt is, Bob referred to it in the Molalla River area, and this is the same lava, part of the same lava. Now we call this lava the Columbia River basalts, and we call that, so it was several different lava flows that occurred over a period of 11 million years.
Let's go back to our cliff exposure in the Molalla River corridor in episode 8 to illustrate the two distinct portions of a lava flow. These are named from Greek architecture. The lower portion is called the colonnade, while the upper is the entablature. The Amity Hills, Eola Hills, and the Salem Hills are fine examples of what we call reverse topography. Reverse topography is where we have a low spot that the lava travels through and solidifies. This is a very different kind of lava than the Cascades. It has a low enough silica content to make it flow almost like a syrup. It takes over river valleys, leaving the softer sandstone ridges to erode. So what was the low spot now becomes the high spot.
And so it flows and it takes over river valleys as it flows along. So what it did is the lava flowed in. I'm showing you my fingers here, and let's call each one of my fingers a ridge, and then the place between my fingers, let's call that a valley. Okay, so the valleys exist and they are the low spot. The lava comes in and flows in and fills those valleys. And then because of differential erosion, because the rock around it is softer than the basalt, it erodes away. So what used to be the low spot is now the high spot, and we call that reverse topography. The Columbia River basalts, as you know, flowed so far, and you have to stop and ask yourself, how could it do this? This is lava, and you all know that lava cools and forms rock. How can it flow that far, all the way from the Idaho border to this spot here? And the answer, you know, I got the privilege a few years ago of being in Hawaii and actually watching the lava pour onto the landscape, Kilauea erupting. And there was, I saw a little finger of lava about maybe this high come over the ground, and it cooled right in front of my eyes. And so you ask yourself, if this stuff cools that quickly, how did we get it traveling this far? It's one of the things that's unbelievable about geology. The answer to that question is sheer volume. The amount of volume, now this was a fissure eruption, so these eruptions were gigantic cracks that opened up in the ground and lava issuing out of it. It was so runny that it couldn't make a mountain. It doesn't make a mountain like other lava will make a cone and make a volcano. And this just flowed across the landscape. But the sheer volume of it was tremendous. Imagine a gigantic crack opening up, and it was estimated that it would fill 2 Olympic-sized swimming pools in each second. Each second you had enough lava to fill 2 swimming pools, and that the sheer volume of it is what allowed it to flow so far. Now, surely it was crusting over, so this is what this lava does. You've got the outside of it cooling and forming a cooling rind and trying to block the lava, but there was so much force of liquid lava coming in behind it that it broke through its own crust and advances across the landscape. So we came up with an average velocity of the flow, which we'll talk about later. But you can't think of it as a steady flowing like water exactly. It crusts over, breaks through its own crust because there's so much volume of liquid stuff behind it, and then advances across the landscape. Now this basalt is, Bob referred to it in the Molalla River area, and this is the same lava, part of the same lava. Now we call this lava the Columbia River basalts, and we call that, so it was several different lava flows that occurred over a period of 11 million years. And collectively we call it the Columbia River basalts, or the CRBs for short. And that's because it used this lava, as Bob mentioned earlier, comes all the way from the Idaho-Oregon border. And it flows all this way to about here. It's about 300 miles from its source where it came out of the ground. And it flows, and as you'll see, it becomes the Amity Hills, the Eola Hills, and then it flows all the way through the Coast Range, and we'll see it over on the coast as well. Now, the Molalla River has the Ginkgo flow, which is a more recent flow than this one. But the Ginkgo flow can be found, if I look across the highway here to the south, capped on the top of a hill, there is some of the Ginkgo flow, the same flow that goes through the Molalla River corridor.
So let's go visit that flow and witness the source of Jory soil, which grows the best grapes at one of Oregon's finest wineries.
I'm Steve Anderson. I'm the winemaker for Eola Hills Wine Cellars, and we are at our Legacy Estate Vineyard just outside of Rick Rial in the Eola Amity Hills. So behind me you'll see the hillside, the Eola Amity Hills. This is important. At the top we have really red clayey soils. That's that Jory series. As we come down, as those soils decomposed and mixed up with the underlying soil types, we have colluvium. And so we have Jory, Nikaya on the far side where the spring has eroded all the topsoil and exposed just a pure marine sedimentary layer. That is key to where we planted what and why, and then I make different types of wine.
Our next stop is at the top of the hill where we join Sheila, already describing how Jory soil is created from the weathering of Columbia River basalt.
Here are these round rocks, and they've got layers. You can see layers all the way around. They look like cabbages poking out. You can see gradations here of the weathering and this decomposing. This becomes the Jory soil.
To see how each of these rounded shapes formed, let's use an example from the quarry to illustrate how each column terminates in a hexagonal or pentagonal shape. Water and air, called weathering agents, attack each side with a focus on each corner. Over time, this creates a rounded shape. You can see Steve here holding this weathered material, and when mixed with organic compost, forms the official Oregon state soil, Jory, which is only found in Western Oregon.
We're going to leave the vineyard now and continue following the Columbia River Basalt west and south. Although the exact path taken through the Coast Range is uncertain, these ancient lava flows made their final appearance on the Pacific coast near Seal Rock, just south of Newport. So we're here at the Seal Rock, which is about 10 miles south of Yaquina Head. This is the most southern part of the Ginkgo flow, and the exposure here, this is called Elephant Rock behind me. This is a state park, one of Oregon state parks here on the beach. And it's really just a beautiful scenery. Not only but again, if you wrap your brain around the fact that what we're looking at here in the ocean, these huge rocks came from the Oregon-Idaho border, which is part of that Ginkgo flow that we've been tracing on our way from Molalla to here. And it just try to wrap your mind around. We drove several hours to get here, and Sheila's gonna talk a little bit about how long it took for this lava flow to get to where we're at here today. So I want to turn this over to Sheila, and she's going to talk about the specifics of what we're looking at here. There's some interesting geologic features that she's going to cover.
This wall of lava that you see here, it looks like, for all the world, like a wall. And what this is the top of a sheet of lava. Just imagine a whole sheet coming up, and this is the eroded remains of it. So these are called dikes because it looks like a man-made wall. Okay, but these are natural features. So this lava traveled its way through the Coast Range and got to the ocean here. And there, as you can see, there's soft sediment everywhere. The volume of lava, this lava actually sank into the soft sediments when it hit the coast. And then so much pressure was behind it that it re-erupted. And so we call these invasive basalts. Intrusive, the word intrusive means it comes from deep inside the earth and moves its way up towards the top. But invasive came from the top, went into the ground, and then re-erupted again. So what we're seeing here is a dike. Look behind you, and that whole row of rocks over here is also a dike, the eroded remains of a dike. And then we have Elephant Rock, which is a sill. It is a layer of rock that's oriented, instead of cutting through the rocks, a sill is parallel with the rocks. Okay, and then all the soft sediments subsequently eroded away. And so this basalt above my head here is part of the Ginkgo flow, the same flow that we see in Molalla, in the Molalla River corridor. And here it is at its terminus in the west on the coast. It didn't stop, this lava didn't stop until it contacted the ocean. And then it did an amazing interaction between the soft sediments and the re-erupting basalt. The area from one type of rock to another is called a contact. And this is a good example of a contact between the marine sandstone and the overlying basalt. This is the most southern exposure of the Columbia River basalts along the Oregon coast. And they are found from here, Seal Rock, all the way north. They make up most of the headlands along the Oregon coast, with the exception of one, but most of them are Columbia River basalts, Cape Lookout, Cape Mears, and so forth. Now, the amazing part of all this is when this was first proposed by Terry Tolan and Marvin Beeson from PSU. This was first proposed that this lava, the origin of this lava, actually came all the way across from eastern Oregon. What pins it down is the chemistry. Okay, because even if this lava appears over in eastern Oregon and then it appears 400 miles away here at the coast, if it had come from the same source underneath and had erupted here and then erupted here, it would have been different chemically. It would change as it comes up through the Earth's crust and up to the surface. It would have changed chemically. So Marvin Beeson and Terry Tolan did this chemical testing on it. And by the chemical testing of the rock here and the rock here, they were identical.
From Seal Rock, we're now going to head north through Newport to the Yaquina Head Lighthouse. So we made it to Yaquina Head. This is a famous place, the lighthouse, natural scenic area. Lots of things to see here. Most importantly, the basalt that came from Oregon, Idaho. And I'm gonna turn this over to Sheila, and she's gonna talk a little bit more about some of those things, about the mystery of how it got here and how long it took.
So it turns out studies have been done, and it took a week to get here. So it took a week to get 400 miles. That's moving at anywhere of a velocity of 2 miles an hour to 17 miles an hour. And now just imagine a wall of lava 100 feet high, red hot lava, moving across a landscape, breaking through its own crust and making progress. So this lava is very hot. It's incandescent red, glowing red when it comes out, which is the end of the line and the end of the story. Thank you very much.
On your next trip to the Oregon coast, I hope you'll see Mollalla's front yard with a deeper understanding and a new perspective as you pass through the Amity-Yola Hills and admire the rock formations created by the Columbia River Basalt Flows as they journeyed to the Pacific Ocean.
Thank you for spending time with Welcome Molalla. We hope you enjoyed this episode and that you will come back for more and share with your friends. And don't forget, if you'd like more information from the Elola Hills Legacy Vineyard, check out episode 29 on my YouTube channel, Welcome Molalla, and episode 8 for part 1 of this video series in the Molalla River Corridor.